Okay, so last time we introduced the concept of a random variable. And this time we're gonna talk about a specific type of random variable, which is really very common. A lot of different, real world problems can be modeled using binomial random variables, as we're gonna see. Okay, so before I tell you about binomial random variables, I need to introduce an even simpler, a very, very simple type of random variable called a Bernoulli trial. So an experiment with only two outcomes is called a Bernoulli trial. Very standard example is a coin flip. Okay. So when you flip a coin, you've got two possible outcomes, and in this case, they're both equally likely, but they don't have to be equally likely for a Bernoulli trial, so they could have different probabilities. So for example, if you roll a die and all you care about is if it's a 3 or not a 3. Right? So if all we care about is if it's a 3 or not a 3, then there's really just two possible outcomes. Either it's a 3 or not. Right? And they have different probabilities, right? The probability of being a 3 is 1/6. The probability of not a 3 is 5/6. Another kind of more real-world version or experiment could be, playing a sports match, and you either win or you lose, right? So if we assume there's no probability of a tie, if it's always a win or a loss, that's a Bernoulli trial. Okay. So when we're talking about Bernoulli trials, we usually think of, we've got two outcomes. We usually think of one of them as being like a success and one of them as being a failure. So we usually call the two outcomes success and failure. And the notation we use is, the probability of a success, we usually write as P. So where P is just some number between 0 and 1. If the probability of success is P, and there's only two outcomes, what's the probability of failure? Yeah. Well, yeah, in a sense. So this P isn't representing an event, it's just representing a number, but it'll be 1 minus P. So yeah, the failure is like the complement of the event success, right? When you take something and its complement, the probabilities need to add up to 1. So the probability of success is P. The probability of failure is 1 minus P. But we often write, so there's a little bit, like the notation is, I mean, there's nothing wrong with this, writing this as p and 1 minus p, but it looks a bit asymmetric because, I don't know. So we often write that the probability of failure is q, but here when I say q, like q is 1 minus p. But sometimes it's more convenient to say, okay, the probability of success is p, the probability of failure is q, but you need to know that this q is not, it's not independent of p. The q has to be 1 minus p. Yeah? So if you write, so this p is just a number. For example, like if we're in the flipping a coin situation, this p would be 1/2. You wouldn't normally write something like 1/2 prime or something. So this p is not a set. It's not an event. It's just a number, right? So yeah, but that's a good question. Yeah. Any other questions about that? Okay. So this is just a Bernoulli random variable. Basically, you just have two outcomes, and they have some probability p of success, probability q of failure. A binomial experiment is a sequence of Bernoulli trials so such that, so there's a few kind of rules they need to follow. So the first rule is that the number of trials which we usually denote, so denoted by n, is a fixed number. Okay? So the number n, it can't depend on the experiment. Like, we'll do an example to show what I mean by this. But basically, it's got to be like you're doing 100 trials or 10 trials or whatever. The n can't be kind of, it can't change depending on the outcomes. Second property is that every trial has the same success probability let's say p. So you can't say, okay, I flip a coin, it's a success if it's heads, and then I roll a die. It's a success if it's a 3. And then I flip a coin, and then I roll a die. Like those are all having, getting a heads has probability 1/2. Getting a 3 has probability 1/6. You can't mix and match these different probabilities. They've got to all have the same probability. And thirdly, the trials have to be independent. Okay. So you can't keep doing trials and then say, have the fifth trial depend on the fourth trial in some way. They've got to be independent trials. Okay. This is all quite general, but hopefully we can see what all of these conditions mean when we do a few examples. So a very standard one, flip a coin 10 times. Each flip is considered a success if it is heads. Okay. So I guess here I guess my question is this a binomial experiment? And if it is, and then if so, what are N, P, and Q? So to know if it's a binomial experiment, you just need to know that whether it satisfies these three conditions, right? Okay. So is anyone, who thinks it is a binomial experiment? Who thinks it isn't? Okay, it definitely is. So, and so what are my values of N and P and Q? So N is the number of trials, right? It's going to be 10. P, the success probability is a half for each trial. The failure probability is a half, right? So this is a very, very standard one. And basically all binomial experiments should be kind of like this, that you think of it as a bunch of kind of coin flips or something like that, where each coin flip doesn't depend on the previous ones. And like maybe if it's not a coin flip or something, you might have a different value P and Q, but yeah. Okay. Let's look at another one. So here, I'm going to say flip a coin repeatedly until you get a heads. And then once you get a heads, you stop. Okay. So who thinks this is a binomial experiment? Who thinks it's not a binomial experiment? Okay. What's the problem with this? Why isn't it a binomial experiment? Yep. Exactly, yeah. So this is what I was trying to get at with this condition. And so yeah, it's good that you can see that from this example. The number of trials is not a fixed number, right? Like if you just read this experiment, the number of trials could be anything. It could be one, it could, maybe you get a heads the first time, or maybe you get tails then heads, or tails, tails, heads. The number of trials could be anything. So the number of trials depends on the experiment. Okay. Right. Let's do another one. So take two cards. From a standard deck. Without replacement. And now each card is a success if it is an ace. Who thinks this is a binomial experiment? Who thinks it isn't? There's a lot of people still thinking about it who aren't sure. Didn't see very many hands on either of those. I don't know, what's, depending on whatever your opinion is, like, does anyone have an argument either way? Yeah? Yeah, exactly. That's exactly what I'm looking for here, right? So actually, I think the first two criteria here are satisfied, but it's the last one, this independence criteria, that's violated, just like you said. So that's a perfect explanation. So this time, yeah, like as was said, this is no, the trials aren't independent. Okay, and just like as you said, so for example, if the first card, if the first trial, let's say, is success, then the deck has fewer aces in it now. So then the second trial is less likely to be a success. Right? So these trials actually affect each other. Okay. However, if this was with replacement, if I take a card, look at it, put it back, shuffle, take another card, that would be a binomial trial. That's okay. So to repeat, this violates the third condition. Any questions about that one, or that one's a bit more subtle? It takes a bit more thinking. Yeah. It would qualify if it's with replacement, yeah. As long as you put it back and then shuffle it and you don't know where that card is or whatever, you take another one. Yeah, because both times you'd have like 4/52 chance of getting an ace. And then you put it back, and now basically if you put it back and shuffle it, that resets the whole experiment, and now it's like you got the same, you again have a 4/52 chance, right? And it doesn't depend on the previous one. Okay. Okay, for something that violates the second condition, I guess it could be something like I said before, like if I flip a coin, it's a success if it's a heads, and then on the second round, I roll a die and say it's success if it's a 3. That would violate the second condition. Okay. All right, let's do an example. Or okay, sorry, this is just another example where I'm asking you, is it binomial or not? So let's say 70% of UVic students have a Netflix account. Although maybe this is outdated. I don't know if people watch Netflix anymore, but sorry? What was that? Oh, okay, missed that. So select two students at random. And let's say each is a success if they have Netflix, right? Okay. So who thinks this is binomial? Who thinks it isn't? And a lot of people are still kind of processing. There is a bit of ambiguity in this question, I have to say, but this is something you're going to see in a lot of questions. I mean, I've looked through old tests and stuff. I feel like these questions are ambiguous because it's not telling you if they pick the students with replacement or without replacement. And that makes a very small difference, right? But when you see questions like this, where you're taking two people from a big body of students or whatever, you should think of it as you're doing it with replacement. The questions won't always say that, but okay, and this goes for MyLab Math as well. They won't always tell you if it's replacement or not, but essentially though, UVic has a lot of students, right? If I picked them with replacement, the chances of getting the same student twice is pretty low anyway. So anyway, so if we're assuming this is with replacement, what would is this binomial or not? Yes, I see, yeah, thumbs up, right? So this is binomial. So this is yes, where your P is going to be 0.7, Q is 0.3, and N is 2. Okay. All right. Any questions about that? All right. Okay, so another definition. So given a binomial experiment, if x is the number of successes, then we call x a binomial random variable. Okay. So for example, we can roll 4 dice. and let x be the number of 2's. That are rolled. Okay, so then x is a binomial random variable. With, p is going to be 1 over 6, right? Because we think of, so x is the number of 2's. So we think when we roll the die, a 2 is a success. Q would be 5 over 6. And n is 4, right? Because we're doing 4 trials. Okay. So what I want to do now is come up with a formula for events involving binomial random variables. Like, figure out a formula for the probability that a binomial random variable is equal to a certain value. Okay, and let's do it just for this example, and then we'll kind of look at what it would look like more generally. So in this example, if we wanted to compute the probability x is 0, this is something we already know how to do, right? So we would normally we would take, the bottom is the number of total number of outcomes, and on the top we've got the number of outcomes where none of them roll a 2, right? And note that you can think of this as like, another way to think of, so this is correct, but another way to think of it is like, so these are independent rolls, right? So how many ways can we have 0 successes? Well, the first one has to be a failure, and then the second one has to be a failure, and those are independent, so the probabilities you can just multiply, right? So you can also think of this as, it's 5 over 6, so which is the q times q times q times q, because you have to fail 4 times, right? And all the trials are independent, so you can just multiply them, right? Okay, so the probability of no successes is pretty easy. They have to all be failures. This is a bit different, right? If we want exactly 1 success, so I'll kind of write this out as like, it could be a success and then 3 failures. Or a failure, success, failure, failure, or failure, failure, success, failure, or it could be 3 failures and then a success. Right? And again, all these things are independent, so the probability of this would be like, probability of success times probability of failure cubed. Because when things are independent, you can kind of split them up. But if you think about it, all of these are the same, right? They're all probability of 1 success and 3 failures. So I've got 4 times this, right? So it's 4 times p times q cubed, which in this case is 4 times 1 over 6, 5 over 6 cubed. Okay. What I'm trying to eventually do is come up with a pattern here. In order to make this pattern a little bit clearer, instead of writing a 4 here, I want to kind of think of that as 4 choose 1. So this is something we were able to compute before, right? The number of ways to have one success. There's 4 choose 1 ways to pick which is a success. And then the probability of a success is 1 over 6. Probability of failure is 5 over 6. And that has to happen 3 times. Is everybody with me so far? Or any somewhat? Okay, so maybe without going through all of this detail, can anyone see what probability x equals 2 is going to be? Yeah, I think I missed the first part, but was it 4 choose 2 or? Yeah. Sorry, I just yeah, didn't hear the first part of what you said. But yeah, exactly, that's what you want. You want, right, 4 choose 2, which means, you know, if I want a sequence which is like 2 successes, 2 failures, the number of ways to do that is the number of ways to choose 2 positions to be successes, right? If I've got 4 things, if I choose 2 of them to be successes, there's 4 choose 2 ways to do that. So if I wrote this whole thing out with 2 successes and 2 failures, I'd have 4 choose 2 of them. 4 choose 2 is 6, by the way, but each of them has this probability of happening, and so I've got something like this. And then similarly, probability that x equals 3 is 4 choose 3, 1/6 cubed, 5 over 6. Oh yeah, and there's one more. Probability x equals 4 is 4 choose 4, 1/6 to the 4. 4 choose 4 is just 1, but yeah. Okay, so this actually, this is a sort of general formula here. And if you think about it, just by thinking of things in the same way, we can get a general formula for any binomial random variable. So if x is binomial, like a binomial random variable with n trials and success probability p, then for any k, the probability that x is equal to k is n choose k, p to the k, 1 minus p to the n minus k. Or in other words, it's p to the k times q to the n minus k. right? Because remember, Q is 1 minus P. Okay? And the way to prove this is exactly the same principle as this example. You've got n trials. We need to choose k of them to be successes, and choose k ways to do that. And then the probability that each of those successes happens is p. So we've p to the k, because they're all independent. Then we've got q to the n minus k for all the failures. Okay. Any questions about that? So this is really just a formula you can plug in numbers into. Okay, and this is for k. So sorry, this board is, we're really at the bottom here, but so this only makes sense for values k from 0 up to n. Because if you do n trials, you can have 0 successes or 1 success, blah, 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 up to n successes, right? Okay. So another example. A factory which produces, so a factory producing, let's say, hockey pucks. Let's say makes mistakes on the pucks. I don't know what a mistake on a hockey puck is, but let's say 1% of the time. And I guess we assume that these are kind of independent. So every puck has a 1% chance of being wrong. So out of 400 pucks, what's the probability that 6 of them, exactly 6, have mistakes? So really, 90% of like your, I don't know, mark or whatever is going to come from just recognizing, oh, this is a binomial with some, well, it depends what you want to think of as success or failure. Let's say a success, weirdly enough, let's say a success is a mistake. But it doesn't really matter which way you think of it. Well, okay, maybe not 90% of your mark is from that. So basically, all you have to do here is recognize this is a binomial. I know the value of n, I know the value of p, and the value of q. And I remember my formula, and then I just plug it in. So this is binomial with n being 400, right? That's the number of pucks, so that's the number of trials. Let's say that we consider a success to be a mistake. So p is 0.01, q is 0.99. And then we just compute the probability that x is equal to 6, which is 400 choose 6, p to the, well, so p is now 0.01 to the 6, 0.99 to the 394, which gives you approximately 10%, so like 10, so 0.10446. Okay. Okay, and it really is that simple. So it's all about just recognizing the pattern of like what a binomial trial looks like, right? Any questions about that? Oops. Okay, so maybe that could have been part A, and let's say we want to do another question. So what if I asked you in the same example, what is the probability that x is at least 2? So probability that there's at least 2 mistakes out of 400 pucks. Any ideas how you might start? So that's going to be really good. If I wanted to get exactly 2, that'll be good, but we want to get at least 2, yeah. Yeah, that's going to make your life a lot easier to use the complement rule. Did you have another? Yeah, so I think you guys are both saying the same thing, which is, you know, to get at least 2, you have to not get 0 and not get 1, and then everything else is fine, right? So this is using your complement rule. The complement of at least 2 would be either 0 or 1. Right, and then now that we have we're doing exactly equal, we can now use what you were suggesting before, which is use our formula. So that's 1 minus 400 choose 0, 0.01 to the 0, 0.99 to the 400, then minus 400 choose 1, 0.01 to the 1, and then 0.99 to the 399. Sorry, I know that's not visible to everybody, but it's 0.1 to the 1, 0.99 to the 399. Which at the end of the day gives you something like 0.90952. Okay, so it's about 90% chance that there's at least 2 mistakes. Okay. Any questions about that? Okay, if you really wanted to, you could have added up, like, you could have done 2 mistakes plus 3 mistakes plus 4, all the way up to 400. You'd get the same answer, but you don't want to do that, right? So let me just kind of end on something which is maybe kind of surprising at the start. So like, remember, probabilities, if you add up if you add up probabilities of all possible outcomes, they're supposed to add up to 1, right? So one thing that might seem a bit concerning is, like, we've got these, like, if we've got this weird formula that the probability that x is k equal to k is n choose k, p to the k, q to the n minus k. So if I add this up over all the possible values of k, it should give me 1. If it doesn't give me 1, there's something wrong with the universe, right? Like, if you add up all the possibilities, they should give you probability 1. And it seems like a very strange formula. Like, why would if I take this strange formula, I add it over all values of k, why the heck would I get 1? It seems a bit kind of, maybe a bit suspicious. So let's say if I take the probability x is 0 plus the probability x is 1 plus the probability x is equal to n. So what I get is n choose 0, p to the 0, q to the n, plus n choose 1, p to the 1, q to the n minus 1, plus dot, 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 all the way up to n choose n, p to the n, q to the 0. Does anyone remember something like this? We didn't practice it very much, and it didn't show up on the test, but we've seen something that looks kind of like this before. Yeah, this looks a lot like the binomial theorem, right? Except before we had like an x and a y, but x and a y could just be p and q. It doesn't matter, right? So what the binomial theorem says is that this big sum should be equal to p plus q to the n. Because remember, the binomial theorem was for expanding things like this. So when you want to expand this, it gives you something like this. But what's p plus q to the n? Remember, q is 1 minus p, right? So that's p plus 1 minus p to the n, so it's just 1 to the n, which is 1. So there's nothing wrong with the universe, right? The sum of the probabilities does equal 1. Okay? Any questions about that? Yeah? Because if I want n successes, so it's going to be kind of p to the n. So q to the 0, one thing to notice is like anything to the 0 is just 1. So yeah, exactly, yeah. All right, so have a good weekend.